Today we're gonna start talking about the very fundamental things about the motion chapter. So, which is called kinematics and dynamics. Individually, they have two different names. Kinematics is the part of study of physics which deals with uh, objects which are at motion, which are stationary, and the reasons for their stationary or conditions for being stationary. So, for example, what do you mean by equilibrium? What should happen at equilibrium? How could we possibly achieve equilibrium? What is the distribution of forces at equilibrium? If an object is at an equilibrium case, then how can we show the forces in vector diagrams, so on and so forth, etc., etc. And dynamics, on the other hand, deals with the part of the physics which works with variables or conditions when an object is already in motion. For example, if an object is already in movement, then what is the reason that the movement would be sustained? Or should the object eventually decelerate to rest? Or should the object keep on accelerating forever? Or in the case of the movement, how does the forces work? Uh, what is the effect of air resistance? Is there any, or are we considering it negligible? How can we find out the total distance covered over a certain duration of time? How does the acceleration changes with respect to time? How does the velocity changes with respect to time? So these motion parameters, as they change or remain unchanged with respect to time, this is something that we discuss in the dynamic spec in chapter. In your syllabus, if you turn up your syllabus, you'll find that kinematics and dynamics are divided into two different parts. I don't usually teach these two chapters individually or differently. I simply teach a single idea-based chapter, which I call motion, or sometimes this is also called force, acceleration, motion, which basically deals with both of the parts, because the borderline between kinematics and dynamics is actually very blurred. So you don't essentially have to understand which question belong to which chapter and which question belong to the other chapter. That is something that you don't have to bother about. I just went through the description of these two topics because they are in your syllabus. So if you turn up your syllabus, you might actually come across these two terms, and so that you are not startled when you see those terms. So these are the name of the topic that we are going to cover. But I'm going to essentially keep on going for the for the progression of this chapter automatically. What we've done up so far, we've done two very detailed class as for what are graphs, how to work with graphs, straight line behavior, curve behavior. We've also seen how to measure the gradient of a straight line. We have also seen how to measure the gradient of a curve for a specific point. We have also seen that. And then we have also seen that how do we describe the graph. No, have we seen how to describe the graph? We've seen the area, right?
Yes.
Okay.
Yes, sir.
Yes, we have also seen the how we have also seen how do we have also seen how do we work with the area for a certain type of graph, and so on and so forth. So today, first I'm gonna show you the the type of the six type of graph that we're gonna usually work with, and then I'm gonna immediately dive into some mathematical process for today's class. So the first thing first is that if you consider that for any type we can usually have basically six different shapes of variable. Actually there can be more than that, but the six different shapes are very primary as far as my experience goes. Let me show you these six different shapes. So let's say this is a certain axis system. I'm not naming these axes at this moment, which I will do eventually, so that we can talk about these stuffs pretty soon. Let's say this is our y-axis, this is our x-axis. So we can have any variable over here. This could be a velocity time graph, this could be a distance versus time graph, this could be a power versus time graph, this could be a force, pressure versus volume graph, blah 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 blah. So we have plotted two interdependent variables on the x-axis and the y-axis. Typically we can have these six different shapes. For example, For the case of increasing graphs, we can have these 6 shapes. So this is a typical shape for an increasing graph. Increasing graph means the type of a graph where as the x value increases, y value also increases. And then we can have curved shapes which look like this. Now, did we discuss these graphs in your lecture earlier? How does the gradient change as x value increases? Did we?
Yes, sir.
Oh, we did. Okay, so then just a quick recap. Might as well finish this pretty fast. So if is question number 1, this is a straight line with a constant gradient. This is curve, let's say number 2. This has its gradient here. The y value increases as x value increases decreasingly means that initially the gradient is pretty high. As you slowly move from to on the right side of the graph, if you try to visualize tangents on this line, for example, if I try to draw multiple tangents on this line with the green, you'll see that initially the tangent will be pretty steep, something like that. Then as you slowly move to the right, your tangent is going to become more slanted and more slanted, for example, somewhat like this, and then somewhat like this over here. So as you slowly go from left to right, you're going to have more and more slanted tangents. So we say that graph number 2 is described that as x value increases, y value also increases decreasingly means the gradient is decreasing or the rate of increase decreases. And the third shape that we can have is obviously the other way around. For example, we can have curves which have a shape like this. These are also increasing graphs, because as the x value increases, y value also increases. You can see that smaller values of x gives you smaller value of y. As you go slowly to the right, you will see that the relevant y values are increasing, which makes sense. But this is the shape where the rate of increase is increasing. Initially, you have a pretty slanted line. The tangents are going to be pretty slanted. As you slowly go from left to right, your tangents are going to be pretty steeper. So we can say that graph 3 is an increasing graph with increasing gradient, or you can say the value of y increases as x value increases, comma, increasingly means that the rate of increases, or the gradient of the graph increases. So these are the 3 different variations for increasing graphs. Vice versa, we can also have similar, not exactly same, shape for decreasing graphs as well. So if we just take out the coordinate system over here for the same coordinate system, and let's say I'm gonna get rid of these lines. So we can have decreasing graphs. First of all, we can have a decreasing graph with straight line, which might as well look like this. This one means that as x value increases, y value decreases uniformly, or you can say with a constant gradient, which means the gradient is a straight line, so the gradient is equal at every single location on this straight line. Or we can have a decreasing graph that has a shape that looks like this. So this shape represents a graph that has where the y value decreases as x value increases. Now try to have a look at this thing. Before I tell you this thing, try to observe how do you describe the change of the gradient of this graph. What is happening to the gradient of this curve as you slowly observe from left to right for this observation with increasing values of x? How does the gradient change? Kids, respond. How do you think?
Goes from steeper to slanted.
Increases.
Okay.
The
Anything
gradient
else?
differs.
The gradient
Differs.
differs. Okay. Okay. Anything else?
Gradient increases.
Gradient increases. Okay. That's another response. Anyone else? All right. Let me tell you this thing very clearly. First of all, I'm going to try to write the description of this graph so that we can all be at the same page. The way we are going to describe this graph, for example, let's say, let me give you numbers. For example, number 4 was as x value increases, y value decreases uniformly. That works. or it has a constant negative gradient. Negative gradient because this, as x value increases, y value decreases. So if you are gonna try the generic equation for a gradient, which gives us del y by del x, at any point if your del x is positive, which means if you consider your x value is increasing from a small to a large value, your y delta y should be negative, because like I told you earlier that delta would always mean change. Change means final minus initial, not big minus small. So you for delta y would be a smaller y value minus a bigger y value. So delta y would be negative. So essentially the entire value of this ratio should be also negative. So whenever we say that, hear me out for this part very carefully. Whenever we say as x value increases, y value decreases, we are already implying the type of change that is happening. So this type of graphs are called decreasing graphs, where as the x value increases, the y value slowly becomes smaller and smaller and smaller and further smaller. So there also we can have three different patterns. Number four is pretty simple. It is a decreasing gradient graph with constant gradient, or or uh, the change behavior might also look like this. Now, to have a look what is happening, I need you to, all of you, to try to visualize this kind of straw figure, or let's say needles, which will be placed onto this line, and try to observe in your head how does the tangent or tangent straight lines are gonna have their gradients as we slowly observe the curve from left to right. How is that gonna happen? So let's say, for the sake of easier visualization, let me just try to draw two of them here, and I would like you to try to visualize the rest of them. For example, the first tangent might as well look like this. The very last tangent might as well look like this. So my question is, if you observe the change of gradient from left to right, what is happening to the value of that gradient? Not necessarily by sign. In terms of value, is this should this gradient be have a larger magnitude, or should this gradient have a larger magnitude?
The first one.
Yes,
The
that's a
first
correct
one.
response. But every one of you, please respond. Either you
The
respond
first one.
or you write in the message window, which works. Either way it works. But do participate in that class. So you have to understand.
First one.
This one has exactly. This one has a much steeper gradient because this is more steep compared to the other line. So if we observe this whole thing from left to right, we can essentially say that the gradient of this graph was decreasing. Gradient of this graph is decreasing. So the way we can actually describe graph number 5, let's say, is that as x value increases, y value decreases with its gradient decreasing. Now, one more thing that I really need to understand, that gradient for this line, the gradient decreasing would essentially mean what? Whenever we are saying that the gradient of a certain graph decreases or increases, we usually exclusively mean what is happening to their we mean that what is happening to their magnitude. We don't usually cover the idea of their absolute sign plus or minus in the discussion of gradient. Let me elaborate what I mean. This line has a this line is more steep compared to this line. So if you draw a right angle triangle over here and draw a right angle triangle over here, obviously this is going to give you a much bigger m value, del y by del x, in terms of magnitude. Let's say the gradient of this line or the curve at this point where this tangent was drawn. Let's say the gradient of this curve over here is minus 10, and let's say the gradient of this curve over here is, let's say, only minus, let's say, minus 0.1. Now try to understand in terms of numbers between minus 10 and minus 0.1, which one is smaller?
Minus
Minus
10.
0.1.
Minus 10.
Minus 10.
Minus 10.
Minus 10.
In terms of number, which is smaller?
Minus 10.
Minus
Is a
10.
smaller,
Minus
more
10.
smaller number.
No, in terms of number, 0.1
In terms
is
of
the
number.
smaller.
Yeah.
0.1 is the smaller.
I didn't say in terms of magnitude, I said in terms of number. But the very basic idea.
Oh, acha.
0.1.
Oh.
No. But the very basic idea of number, more negative a number means smaller a number. Try to think about it. Between 2 and 3, which one is smaller? 2 is smaller, right?
Yes.
But between -3 and -2, which one is smaller?
-3.
-3.
Think. On the number line, it's very simple. As for numbers, not by magnitude, by their original number definition, if you try to plot 2 points on the number line, the one that is on the more left is the smaller one, the one that is on the more right is the bigger one.
Bigger one.
The reason why am I bringing this up? The reason is very simple. If you consider the change of gradient for this case, you can see that while considering their number property, obviously the gradient is increasing because the gradient is essentially changing from here to here. The gradient is changing from -10 to -0.1. For both of the cases, we have negative gradient, but in terms of number, the gradient is increasing. But that is the problem, or that is the information that you cannot write in your case, because that's the key point that I was trying to highlight. Whenever we say how the y value is changing, I mean, is it a positive gradient line or a negative gradient line? We have already determined its sign. So for example, whenever you say that as x value increases, y value decreases, this part essentially means that the entire graph would have a negative gradient. So you have already determined its sign. All that is left to talk about is its magnitude. So in this case, we can say that from left to right, this graph is changing from a more steep graph to a more slanted line. That is a very definitive thing. That is a very pretty simple and I mean unanimous description that on the left the graph is more steep, on the right the graph is more slanted, which means in terms of magnitude, the gradient over here is larger and the gradient over here is much more smaller. So the way we describe this curve, let's say curve number 4, is that as x value increases, y value decreases, and the gradient of the curve decreases. Because in this case, gradient of the curve is essentially meaning the magnitude of the gradient of the curve, but we do not use the term over here because by mentioning that y value decreases as x value increases, we have already implied the minus sign. So let me just write this thing over here just to make a better sense to all of you. How is this becoming larger? This is very weird. What? No. Wow. What? Okay. I can live with that. দেখো এই ডিসিশনটা বোঝা যাচ্ছে কিনা there are a couple of things that I would really like you to appreciate. First of all, is that I have written the that was not the plan. Okay. Acha, I messed up the timing procedure, but bear with me. Have a look. The description reads: as X value increases, Y value decreases. So by I have given this first set of information in bracket because graphs are always described as the X value increases. So we might, in many cases, skip this initial part, or the question also in many cases might say as well skip this part, because graphs are always described. Always in this case mean always described from left to right. So as X value increases, so I could only write for number 5, Y value decreases. Whenever we say I say this part, Y value decreases, I already mean that the gradient of the graph is negative, because in the equation of m equals to del y by del x, one of the top variable is supposed to be negative, because you will be subtracting a small minus a large number. Because I have already specified the sign already, for then in the next sentence I'm going to only talk about its magnitude. So what happens, the gradient of the graph decreases since the graph changes from steep to a more slanted line. দেখো এই ডেসক্রিপশনটা সব বুঝা যাচ্ছে কিনা? If you have any questions, please respond.
Sir,
Yes.
sir, can you draw a right angle triangle to the second gradient?
I can try, but it can be hell of a difficult thing, but I can try. And obviously try, why not? Wait. Okay.
Yes, sir.
আচ্ছা, so দেখো বলবান নাম্বার 5 এর ডিসিশন সব বুঝা গেছে কিনা এভরিওয়ান?
Yes, sir.
Ji sir.
Yes, sir.
আচ্ছা, so what
Yes,
is the
sir.
next type of curve that we can have? The next possible shape of curve can be in this shape, which is basically, let's name it number 6. This is also a curve, but this is also a decreasing graph, so we might as well describe this that the Y value is decreasing and the magnitude of the gradient is increasing, because you can see that for the initial part the tangents are going to be pretty slanted, but as you slowly go to the right the tangents are going to become more and more steeper, and it's going to be quite steep at the end. So we can say that the gradient of the graph increases. So I'll say the whole description number 6 once again, is that as X value increases, Y value decreases, full stop. The gradient of the graph is increasing. So these are the 5 different shapes that we have. Now if you wonder that in which cases should we be using this, or how are we going to use this information? Well, here is the deal. I mean, I told you in our earlier class that not all graphs gradient would give us a useful information, or similarly not all graphs area might also give us a useful information. But let's say I'm going to give you some example where the gradient of a certain object would be available to us, or would be important for us. For example, if you try to draw a VT graph at any given scenario, what is the name of the gradient quantity of the VT graph? What is the name of the gradient of the VT graph? Velocity time graph gradient নাম কি?
Acceleration.
Acceleration না?
হ্যাঁ।
So মনে করো হচ্ছে কোন একটা certain object acceleration আমাদের number 1 গ্রাফটা দেওয়া আছে. It's a straight line that looks like this. Doesn't necessarily have to pass through the origin. Straight line with positive gradient. Then we might as well say as time increases the object speeds up or it accelerates, and the value of the acceleration is constant. Why? Because this is a straight line, so the gradient is what? A constant number. It's not changing over time, is it? No. So for number 1 we can use that description which is as time progresses, or you can choose not to write this. Velocity of the object increases slash the object is accelerating at a constant rate. So that pretty much works for you. What if we had graph number 2 available to us? How would you describe that part? Yes.
স্যার আমার ইন্টারনেটে সমস্যা দেখাইছিল তো স্যার, আপনি যে যে একটা পয়েন্ট দিয়েছেন ওটা একটু আবার রিপিট করতে পারবেন?
কোন পয়েন্টগুলি?
ওই যে কি জানে ইনক্রিজ, ওই যে যখন কনস্ট্যান্ট হয় তখন আপনি একটা স্টেটমেন্ট বলছেন মাত্র।
Acha, what I said that if the shape if the graph of number 1 shows up for a VT graph, we might as well describe by saying that the object is having its speed increased at a constant rate, or you can write that the object is having uniform acceleration. Uniform acceleration means the value of acceleration is remaining same or as time is going by. So that is something you can write. What if we had this shape for our in our VT graph? Then how would you describe this graph? Or how do you describe the graph for a shape like this? What is the physical description for this one?
Acceleration decreasing.
Exactly. The object is accelerating, but the value of the acceleration is decreasing. So you need to understand this idea. In this case, the gradient is decreasing, but what is happening to the exact value of y? Is the value of y decreasing? Pulvan, respond. Is the value of y decreasing or not?
No.
No, sir.
Value of y is increasing.
No, sir.
Increasing acceleration.
But the increasing amount of increase is decreasing over time. So we can say that this graph shows us a situation of decreasing acceleration. Now, for those of you who have a difficult time distinguishing between decreasing acceleration and deceleration, let me help you to understand this easier. This graph might as well mean that the acceleration of the object is slowly reducing. So let's say whenever the object is starting its motion, it's just somewhere over here. We're starting the object to starting to see the object from here. We do not know what is happening over here. We might have some part over here, but I have drawn the graph in this shape, so I'm going to talk about from this shape. So at t equals to something, let's say at the beginning, the velocity of the object was this one, and this is the highest value of acceleration. Let's say if we draw a tangent over here and measure the gradient of the tangent line, we might as well find the acceleration of that object at this time instance. So let's say that value is, let's say, 5 meters per second square. So this graph implies that as time goes by, the acceleration will decrease. So let's assume that with every single, let's say that in the first second the acceleration was 5 meters per second square. Let's say in the next second the acceleration is, let's say, 4 meters per second square. In the next second the object speed was, let's say, 3 meters per second square, something like that. Let's say I am having an uniform decrease of acceleration. The decrease doesn't have to be uniform. I'm choosing uniform value to have us a bit of an ease of calculation. And let's say, just for the sake of interest, I'm gonna show this, that the graph starts from origin. So at 0 second, let's say the acceleration was 6 meters per second square. So try to understand what is happening. As time is going forward, we are having the value of acceleration decreasing. So let's say these are the values of acceleration that I've written. So let's say if I go to write the velocity, let's say at 0 second the velocity was 0. How much was it? At 0 second mark, the velocity was 0 meters per second. That is very evident from the graph. After 1 second, the object's velocity is gonna be 6 meters per second, because from 0 to 1 second is gonna accelerate with 6 meters per second square acceleration. That's for average value, so bear with me. At the 1 second mark, the acceleration has reduced to 5 meters per second square, which means in the next 1 second, the increase of acceleration, the increase of speed would be 5 meters per second. Try to break down the word meter per second square in your head as meter per second per second. Meter per second per second. So try to break it down in your head, because that would give you a much simpler and easily graspable idea that 5 meters per second square means addition of velocity is 5 meters per second for every second. So it means in the next 1 second, which means from 1 second to 2 seconds, this object is going to have some addition of its velocity, but that is not going to be 6 meters per second. How much addition should it get? 5 meters per second. So what will be the total velocity after 2 seconds? This is gonna be
5 meter per second.
5 meter per second is the gained velocity, whereas the after the 1 second, after the 1 second duration, the velocity was 6 meter per second. So it's gonna get another 5 meter per second velocity. So if I keep on
11,
increasing,
11.
if I doing the same thing and go ahead and try to show you this variation, let's say, where was I? This is a bit too big. Okay, I can work with it. So so after the second, the speed becomes this. What would be the speed of the object after the third second? Now this will
13
also increase,
meter.
but it will increase
13
by a value of
meter.
4. এখান থেকে এখানে ইনক্রিজ হচ্ছে কত? 6 মিটার পার সেকেন্ড, এখান থেকে
15.
ইনক্রিজ হচ্ছে 5 মিটার পার সেকেন্ড, এখান থেকে ইনক্রিজ হচ্ছে 4 মিটার পার সেকেন্ড। So this will become
15. 15.
15 meter per second. And I could go on further, but you are pretty much getting the point. So that's what I believe. What I'm trying to show you over here, you can see over here, as time increases, as time goes further, the velocity of the object is actually increasing. Is it decreasing? Have a look. 0, 6, 11, 15. Is it decreasing? No. The velocity of the object is actually increasing. So this graph means that as time goes by, the object is velocity speed is actually increasing. But the rate at which that increase is happening, that value is becoming smaller. So it is having, the object is accelerating, but it is having a decreasing acceleration. So it is, the object is speeding up, but the rate of speeding up is decreasing.
So decreasing acceleration means the velocity decreases, but the acceleration decreases, but the velocity increases.
Exactly.
But in case of deceleration, the velocity and acceleration, both of them decreases.
So I'm going to get into that in a bit. I'm going to bring about all of these curves over here. So I'm going to get into that segment just a bit later. But you're going to get your answer done. But my point is, do you understand the meaning of this thing? That what do we mean by decreasing acceleration?
Yes, sir.
You should not mess up between decreasing acceleration and deceleration. They don't mean the same thing. Deceleration means that actually the object's velocity is decreasing. And decreasing acceleration means the object is still accelerating, but not accelerating as much as it was doing just a bit earlier. As time goes by, the value of acceleration is slowly becoming less and less and less. Okay, so this is a very simple, I mean, this kind of graph is pretty common for the parachutist graph, where we have what the parachutist takes a jump from a high-flying aircraft, and as he falls through the atmosphere, because of air resistance, he has a VT graph that looks like this. So as the person slowly falls down, I'm gonna get into the parachutist graph exclusively, so don't worry. So what if we had a graph that looks like this? For a VT graph, let's say an object had a VT graph that looked like this. How do you describe this graph?
Acceleration increases.
The object accelerating,
Acceleration
is increasing.
Increasing acceleration.
Increasing acceleration.
As well as velocity.
Yeah, velocity is definitely increasing. So I mean, whenever we use the term accelerates, ideally we always mean that the object is speeding up. So the value of the velocity or speed is increasing. So it's a positive addition towards its motion. So the object is accelerating at an increasing rate, or you can say the acceleration of the object is accelerating and the value of acceleration is increasing with respect to time. So that's the description for this one. So these are the 3 parts for the increasing part. For let's go for the decreasing part. Let's say I'm going to use purple. Is it purple? Navy blue? Royal blue? What is the name of this thing? Indigo. Wow. Okay.
You can use red.
Okay. Red is good. So let's say if we try to draw a velocity time graph for decreasing graph, let's say we have a VT graph that has a straight line of decrease. It's pretty simple to describe. We can say that the object is decelerating at a constant rate, which pretty much suffices the purpose. But we are not. So that's pretty simple. What if we had a graph like this? How do you describe the change of acceleration for this curve? Now, first thing first, this graph is a decreasing graph, right? Why am I calling it a decreasing graph? Because as time increases, the value of v is decreasing, which means the object is essentially slowing down. So the object is decelerating. Now, what is happening to the value of the deceleration? Try to observe the gradient of this curve change. How does the gradient of the curve change? Initial gradient
Negative
is high,
acceleration.
and initial gradient of the curve of this curve is, yeah, you're correct. Initial gradient initial gradient of this curve is high, and the final gradient of this curve is low. So the magnitude of the gradient is what? Decreasing or increasing?
Decreasing.
Magnitude of the gradient is decreasing. That is something that I discussed for this curve number 5. So I can say the graph, in this case, the object is decelerating with the value of deceleration decreasing. Or you can say that the object is slowing down, if you want to write it into physical words, not using the term deceleration like that. That the object is slowing down, but it is slowing down more slowly over time. Which means in the first second, let's say it slowed down by, let's say 5 meters per second. In the next second, it might have slowed down by 4 meters per second. In the next second, again, it might have stopped by, let's say 3 meters per second. Then it might be 2.5. Then it might be 1.75. It doesn't have to have a uniform pattern. I chose uniform pattern over here so that I could do the math mentally. That's the reason. But it doesn't have to be this much, or I mean, it doesn't have to be this type of uniform 1 1 1 1 1 gap. It doesn't have to be. So how would you describe this graph? Once again, for the last time, the object is decelerating and the value of deceleration decreases, or you can also write the object is slowing down, but it is slowing down more slowly over time. Are we clear? Are we clear with this description?
Yes, sir.
Yes, sir.
John?
Yes, sir.
So তোমার কি হাত উঠাইছো? Because I have actually minimized your participants list because I was using this part of the screen. You might as well take a look. না আচ্ছা, কার কোনো question থাকলে you can always raise your hand. I'll give you the floor definitely. আচ্ছা, as for the last part, if we have a graph that looks like this, for a VT graph, let's say we have a graph that looks like this. So how do you describe the VT graph for this one?
Increasing deceleration.
Increasing deceleration works. In fact, pretty good. Everyone, try to think about this. Is the object speeding up or slowing down? That's the first thing.
Slowing down.
Slowing down.
The object is definitely slowing down. So the motion
Slowing
behavior is deceleration. Now, what is happening to the gradient from left to right?
Gradient
Decreasing.
increasing.
Increases.
Increases, because once again, if you try to make this kind of straight line, if you try to visualize tangents over here the tangents are going to be like that, and here the tangents are going to be like that. Which one will be more steeper? On the end point.
At the bottom.
On the right, or close to the right end, where this is going to be more steeper. So that's what I'm trying to mean, is that for this scenario, we can say that the object is slowing down, but it is slowing down more rapidly. Or you can say the object is having deceleration and the deceleration is increasing. So as more seconds is passing by, it is slowing down more and more rapidly. So the deceleration is becoming much stronger. That's the idea. So these are the 6 different ways to describe 6 different variation of curves. If you wonder, sir, why is there only 6? I mean, could there be more? Well, to be honest, there can always be a mixture of these 4 graphs. So what do I mean by a mixture of these 4 graphs is something like this. Let's say in a certain given scenario, you can have a combination of graphs that might as well look like this. For example, let's say you are provided with a VT graph. I'm using a lot of VT graphs for my example because VT graphs gradient is acceleration, so it's a defined quantity. So it's easier for me to work with this, but these quantities doesn't have to be VT velocity time graph. They could be for any purpose for that matters. So what I'm trying to mean is that let's say we have a VT graph, and that let's say a certain VT graph has a shape like this. Okay, let's say certain VT graph is finished up to here. Let me try to extend this in a very convenient way. Okay. So let's say we have a graph like that looks like this, somewhat like this. Now, how do you describe this graph?
It's
The object is having increased acceleration at first.
Initially at constant
Acceleration, deceleration, acceleration.
Okay.
and then moving to rest.
It's getting constant.
It's
Did
a
someone
No,
did someone say,
rest,
did someone
rest.
say rest?
It's going to rest.
no, not rest, but constant.
Constant velocity, not rest.
Sure.
Displacement time graph হলে at rest হইতো, ডিটি গ্রাফে at rest হইতো। আচ্ছা, so to be able to মানে properly describe this graph, we might want to divide this graph into convenient segments. So I'm trying to show you what do I mean by convenient segments. Let's say if we start observing from the origin, let's say this is our origin, the graph goes on like that. Let's say just by looking by eye, let's say up to here we have a straight line segment. Then let's say from here we have the curve, and that curve behavior sustains up to here. This curve behavior sustains, let's say, up to here, and from here we have a different curve behavior. Now you might wonder, why am I going through all this trouble? I'll explain. Have a look. Let's say this is O, this is A, this is B, and C and D. So what I want you to understand that these four segments, OA, AB, BC, and CD, they can have different descriptions for their based upon their behavior. For example, the way I'm trying to distinguish the graph segments is that OA is a straight line. So you might as well say that the gradient of the graph is constant. So the initial acceleration of the car was uniform up to a point. From A to B, the object is speeding up, but the acceleration is decreasing. At B, the acceleration is 0. If you wonder why acceleration is 0, because that's the property of the highest or the lowest point of any curve. At the highest and the lowest point, the gradient of the curve becomes 0. Try to think about it. This is the point where the curve is starting to go downwards. So this is sort of a curve, or sort of the highest point for this plateau shape. So if you try to draw a tangent exactly over here, that tangent is supposed to be what? Horizontal. Think about it.
Yes, sir.
I mean something like this. If you try to draw a tangent exactly at this point, that tangent is supposed to become absolutely horizontal. So why is this important for us? Because what I want you to understand, that from here to here, the gradient was decreasing. Then from here to C, from B to C, the gradient is increasing once again. Now you can see over here that the speed of the object is slowing down. So I can describe segment AB and BC in appropriate ways. So I'm going to go for AB first. I can say for AB, the object speeds up less rapidly, and at B point, the acceleration becomes 0. Does it make sense?
Yes, sir.
Everyone, check this out. So I'm going to say it again. From A to B, the object speeds up, or you can say the object continues to speed up, but the value of acceleration decreases, and at B point, the acceleration becomes 0. Acceleration becoming 0 doesn't mean velocity equals to 0. Acceleration becoming 0 does not essentially mean velocity is 0. Acceleration is the fact that represents the change of velocity per second, whereas the velocity is a fact that shows you the actual whether the object is moving or not, or how fast is it moving, that behavior. These are not essentially the same thing. Yes, Farihari Mohsen, you raised your hand. Bolo.
Sir, what happened from O to B, O to A?
Oh, from O to A, I defined it to be a straight line, although I hand drew it. So I said that the object accelerates at a uniform value, or you can say from O to A, we have uniform acceleration.
Thank you, sir.
Sure. So AB পর্যন্ত decision হওয়া বুঝা গেছে কিনা?
Yes, sir.
Yes, sir. So I tried to choose the C point in such a way so that for this segment, the shape is sort of like 6. So here, I tried to choose the C point in a way that this is the endpoint of the decreasing gradient, and this is the continuation of the increasing gradient. So the way I might describe the BC part, over the BC segment, the speed the object decelerates, and the value of deceleration increases, because you can see that initially the gradient should be 0. As I go from B to C, the gradient of the gradient of the curve should increase. Now I'm only using the term increase because by the gradient of the curve, I'm meaning the magnitude of the gradient of the curve. So the line is becoming more steeper, so the gradient of the curve is increasing. So I'll go again. From B to C, the object is decelerating, and the value of deceleration is decreasing. Or in other terms, you can say from B to C, the object is slowing down, and the rate of slowing down is increasing. Or you can say it is slowing down more rapidly as time goes on. More rapidly means that initially it was slowing down slowly, then it was slowing down more rapidly. So its rate of slowing down got increased. That's what it means. দেখো বুঝা যাচ্ছে কিনা? I'm describing this graph continuously. If you have any question, raise your hand and then I'll take your questions. Don't worry. Just don't ask the question immediately. Let me explain it all the way. From C to D, the gradient of the graph is increasing once again. So I can say from C to D, the object is decelerating, but the value of the deceleration is decreasing because the gradient is decreasing. Or you can also say that from C to D, the object is still slowing down, but the rate of slowing down has decreased, or it is slowing down less rapidly compared to earlier. So that's one part. Then from D to, then if I go ahead to divide this part equation further, I can see that there is also a change of variation of speed over here. So let's say this is the transition point where the graph changes shape. Let's say I'm going to name this point E, and let's say here is this point where the graph starts to become horizontal once again. Let's say this point is named as F. So what are the different parts that we want to see here? I might as well say that from D to E, the object speeds up / accelerates, and the value of acceleration increases because for this segment, the gradient is increasing. Then from E to F, the object is still speeding up, but the gradient is decreasing, which means the object is not speeding up as much as earlier, but it is still speeding up because velocity is increasing. From F to all the way to the last point, let's say that point is G. So I can say FG is a horizontal line, which proves that the object is moving at constant velocity. Hence, acceleration is 0. We can call this uniform motion. Okay, I'm done for my description part. If you have any question, raise your hands or start asking. Better you raise your hands. I'll give you floor one by one. Bolo. Yeah, Fabi Harim.
Sir, what happens from A to B? I didn't understand.
A to B.
Yeah.
Look, I'll help you understand. What is happening to the gradient of the curve? How do you describe the change of the gradient from A to B?
Sir, I don't know.
Okay, let me help you. Try to visualize the individual tangent over here, or what I did call the straw figure, something like this. So try to visualize multiple different needles placed on the segment AB, and try to judge their gradient as you slowly move from A to B. What is going to happen to their gradient value from A to B?
It's going to increase. It's going to increase.
Increase or decrease?
Increase.
That's where you are slightly wrong. Let me show you why you are wrong. I'll help you to understand this. Don't worry. It's perfectly good that you're making mistakes because that's what classes are all about. So let's say at the beginning part, our tangent might as well look like this. Not this one, a bit more slanted. Let's say at the beginning part, our tangent might as well look like this. As you slowly move to the right side, how would our tangent change? Shouldn't this tangent become, so this was green, let's say, then I go for pink, why not? Then this tangent is gonna be somewhat like this.
Right.
Then at the B point, the tangent is gonna be what? Somewhat like this. Straight line. So if you observe the individual tangent of the individual value of the gradient of these lines, green, purple, and pink, how do you say that their value, their slantness is changing? Is it becoming more steeper or less steeper?
It's becoming more steeper.
No, steeper means more vertical.
Yeah.
So if you observe from here to here, it is becoming more slanted.
Right.
I'm talking about the alignment of the line, not the position of the line.
Right.
So if you try to produce a triangle over here, this will give you a value like this. If you try to produce another triangle over here, this will give you a triangle like this. You cannot even produce a triangle over here because this was drawn to be a straight line. So the value of del y by del x over here should be bigger. Over here, it should be even smaller. And more smaller, further smaller.
Why, sir? I didn't understand.
Because this line initially was like this. So if you draw a tangent like this, you're gonna get some value where this is the longer part, this is the smaller part. A bit later, the tangent become like this. So now if you draw a right angle triangle, it's gonna have a shape like this. As you're slowly moving to the right, this is becoming more and more slanted. So you're having
Oh. Oh.
now
Yes, now I understood.
beautiful, beautiful. As long as it makes sense, beautiful. I always appreciate questions. So keep coming with questions. এখন বুঝা গেছে কেন হবে এটা?
Yes, sir.
Beautiful. So as from A to B, the gradient was decreasing. Okay. Yes. Sumaya.
Sir, will you please explain C and D again?
Oh, I try to understand C to D as the okay. I'm gonna say just say both the distribution that I used. Just a second. I could say from C to D, the object is the velocity of the object is decreasing, and deceleration value is also decreasing, because this part of the graph is somewhat like this, which resembles to the shape of number 5 graph, where the gradient of the graph is slowly becoming less and less and less, because you can see at the lowest point the gradient is once again becoming what? 0. So you're losing gradient for C to D. Initially you have a more steeper part, which is more vertical, and as you slowly move from C to D, the graph is slowly becoming more horizontal.
Yes.
বুঝতে পারছি?
Yes, sir.
Okay. Everyone,
From B to C, it has an increasing deceleration.
once again.
From B to C, does it have an increasing deceleration?
Exactly. Yes,
Thank you, sir.
R3.
Sir, could you explain E to F?
E to F is very much similar as A to B.
Okay.
Same thing. Check this out. So it's the same description for E to F and has the same description as A to B. বুঝতে পারছো কি?
জি স্যার।
Uh,
স্যার
should-
দুটোটা কি ইউনিফর্ম হবে?
Nah. We are having a variation of the curve, so you cannot use the term uniform over here. The only two places where you can use the term uniform is for this segment and only for this segment. In this case, you can say uniform acceleration. In this case, you can say uniform velocity. Apart from these two segments, for all the segments are curves, so you cannot use the term uniform at all.
Okay, sir. Thank you.
Sure. Yes, Shahrin, go ahead.
Sir, could you explain the part from B to C?
Try to observe what is happening to B to C. At the B part, the gradient of the graph is nearly horizontal. Nearly, no, it's perfectly horizontal. So you have 0 gradient over here. As you move from B to C, the graph is becoming more steep. So this graph has a shape that looks somewhat like this. So you are having your gradient increased. Initially, you have a 0 gradient. Then as you slowly move to the right, you try to draw those tangent line or needles onto the curve. You see that the lines, the tangents are going to become more steeper, or they're going to become more vertical as you observe from left to right. I could draw those tangents just for your visualization. No big deal. I'm not messing it up over here because it's already pretty messed up. So that's why I took this segment out. So don't bother that. So let's say the tangent initially was horizontal, so something like this at the very starting point. Then if I try to draw it over here, I can draw another line. Let's say that might as well look something like this. So let's say that is the gradient over here. Then if I try to draw the gradient at the very last point, that might as well look like this. So try to consider how the gradient is changing as you slowly move from left to right. Here you have a 0 gradient. Here you have a much bigger negative number, even a bigger negative number. So you are having the magnitude of the deceleration increasing. So we would say that the from B to C, the object is decelerating with an increasing rate, or you can say it is slowing down more rapidly.
Thank you.
Sure. Yes, Samir Anis.
Sir, can you
Hello,
sir,
Samira.
can you explain why at B the acceleration becomes 0?
Oh, because the graph graph is changing direction. So it is the highest point of the graph. So I mean, try to have a look. I mean, if I just take this part over here, the gradient was decreasing, and here the gradient becomes 0 because at I mean, if you have any of the highest point of a graph, for example, a dome shape like this, for example, a dome shape like this, or a lowest point, for example, a trough like this. At this point, the gradient is, tangent is always horizontal. At this point, the tangent is always horizontal, because this is the point where the tangent starts to change its value. Through this whole segment, the tangent used to be positive. From a high positive value, it slowly reduced to zero value, and from this point further, as we move from here to here, the tangent slowly becomes more and more negative. So this is the transition point. Because this is a upward curve, that's why the tangent is zero. I mean, try to think about it. If you try to draw a tangent at this point, how would the tangent look like? Should it be like this or horizontal? Try to visualize that. Do I make sense?
Yes, sir.
Beautiful. Yes, Shaptoshi.
So my question is that acceleration of any particular point, can we consider it to be zero?
It can be zero, but I'm not sure what do you mean by considered. Observing the graph, it can be defined to be zero. For example, for this graph, instantaneous acceleration at point B and point D is zero. But everywhere else and also for the entire segment of FG, the acceleration has a zero value. But for all the other points, the acceleration have non-zero values.
So, for the point at A?
Yes, we have acceleration because the gradient of the curve over here is not zero.
Sir, but we don't have any change in velocity, right?
We do have change in velocity. The velocity, I'm talking about instantaneous velocity. I mean, if you consider exactly at point A, I mean,
I was talking about exactly at point A.
Well, exactly at point A means we cannot essentially both the same. I'm getting to your question in detail. Bear with me. We cannot talk about the acceleration of an object for a time instance, because that would not work. Because by definition, acceleration is given by what? Del V by del T, right?
Yes.
If you consider for a time instance, then del T is supposed to be zero. Acceleration is supposed to be infinite, which doesn't work out. To have an observation of acceleration of an object, you need to consider a small, even a very small duration of time, slightly before and slightly after. Only then can you talk about the acceleration of that point. Instantaneous acceleration can be the acceleration of that exact time being, but to determine that, you need to have access to the value of before and after. For example, if I tell you a single point of information, let's say a car's velocity at t equals to 25 seconds is 20 meters per second. Now, only from this information, you can never say whether the car is accelerating or decelerating. Exclusively from this much information, can you say anything?
No, sir.
You cannot. But if I tell you that the car's velocity at t equals to 19 seconds was 19 meters per second, sorry, let's say I'm going to write this down because I'm messing it up. Let's say if I tell you that at t equals to 24 seconds, the speed was 19 meters per second. At t equals to 25, it was, let's say, 20 meters per second. And let's say at t equals to 26 seconds, so I'm using the time instances uniformly so that we can have a comparison. Let's say the speed was 20.3 meters per second. So let's say we have these three values. Now you can essentially say that the object is actually accelerating, because you can see that as time goes by, you're having the values increasing. Do I make sense?
Yes, sir.
So exactly, exclusively by the information of instantaneous velocity, you cannot essentially say whether an object is accelerating or decelerating at that time instance. You need to have a bit of earlier or a bit of and also a bit of later values to compare. And then again, I have intentionally wrote these velocity values with non-uniform increase. For example, here the increase was how much? 1 meter per second. Here the increase is how much?
0.3.
0.3. So you can see that the object is accelerating, but the value of acceleration is not same. What is happening to the value of acceleration?
It's in a decreasing rate.
Beautiful. So we might as well say the object is accelerating, but the acceleration is decreasing. So object is speeding up, but it is speeding up more slowly as time goes forward. Could I answer your question?
Yes, sir.
Beautiful. Farviha.
Sir, isn't B just a point like A is? Why can we tell what B is like if we can't tell what A is like? B is just a time instance to a particular time instance.
Exactly. And I mean, all of these point segments that I have tried to label over here, they essentially represent a time instance. And I have chosen these points based upon they are being, I mean, all of these points happen to be a certain transition point of change of its velocity behavior. Transition point means from O to A, where the motion was uniform acceleration. From A, the graph is starting to take a bit of a curve. That's how I describe the graph. So you are now starting to have the value of acceleration changing its value. From A to B, we have positive acceleration decreasing. Then from B to C, we have negative acceleration increasing. Then from C to D, we're having negative acceleration decreasing. So we are having different variable changing differently for all of these individual segments that I have labeled.
But sir, you said that we don't know what happens exactly at A because it's a particular time instance. Why can't we tell what happens exactly at B?
We can tell what is exactly happening at B.
Yeah, but why?
Oh, because the graph is showing us that this is a curve. This is the highest point of the curvature. Oh, sorry, Reem, let me clarify your question. I got your point. The point that I was trying to highlight in my earlier decision is that to make sense of this term acceleration, this delta t cannot be zero. If this delta t is considered to be zero, then essentially mathematically this acceleration value will become infinite. So you need to consider the value slightly earlier and slightly later to get an idea about what is the acceleration of at that instance. Now, how much earlier and how much further forward, that is a question of the accuracy of the graph or the precision of the graph that you're going to work with. That's where calculus comes in. But you can say what is the exact acceleration of the B point by observing the graph for how does the shape changes.
So if the shape didn't change, would we be able to tell what happens at B?
Exactly, we could. For example, for example, if you consider for the segment of O through A, the acceleration value that remains same from O through A. So if I do label another point over here, let's say if I label a point over here at X and if I label another point over here as Y, I might as well say that the acceleration at O, Y, X, and also at A, all of the four acceleration values are exactly same. I can say that.
Sorry, I understood now.
Beautiful. I actually chose these points O, A, B, C, D, E, F, G in terms of the convenient transition point that where certain parameters of the velocity are changing significantly. That helps us to segregate or make particular segments of the graph, which makes the explanation far too easier to happen. Or if you just dropped your hand, did you get your question answer? What you were about to ask?
Yes, sir, I got it.
Oh, beautiful. Now, Oritri, you just raised your hand and then I just saw that you dropped your hand.
Oh, sorry, that was just missing.
Asha, now we will. Sumaya, yes, go ahead.
Sure, will you explain the acceleration from D to E?
Which
Sir?
segment? Come again, which segment?
D to E.
Oh, D to E is, you have a look. How do you describe the acceleration at D?
0.
How do you describe the acceleration at E?
It increased.
It increased, which means it become more positive, right?
Yeah.
Beautiful. So that's what you say. From D to E, you can see the velocity is also increasing because D represents a lower velocity on the velocity axis, and E is the higher velocity. So we can say that from D to E, the object is accelerating, and the value of acceleration is also increasing.
So from E to F, it's also increasing, right?
Velocity is increasing, but acceleration is decreasing.
Sure, will you explain that?
Yeah,
Like
sure.
the acceleration is.
Yeah, have a look. At the E point is located further below compared to the F point on the y-axis. So let's say at E point, the velocity is, let's say 30 meters per second, where F might as well be 50 meters per second. The object is speeding up, but the rate of speeding up is becoming less. Because you can see over here, the gradient will be more steeper if you slowly move to the right and try to visualize this needle figure. That's the term that I use to make sense. You would see that for this segment, we're gonna have those gradients becoming less and less and less, something like these three triangles. So it is accelerating, but the value of the acceleration is decreasing. So you're having increase of velocity, but the amount by which you are incrementing for equal time intervals, that is becoming smaller.
So at F, it's completely horizontal.
Yeah, that's what I'm trying to draw, that from F to G it is completely horizontal. So at F the acceleration has become 0, and from F to G it is maintaining 0 acceleration, which means it is maintaining an uniform velocity, or we can say that the acceleration is constant, which is 0. This also means a constant acceleration. You have to understand that 0 is also a number.
Yeah.
So it is also, it can be defined as uniform velocity, whereas OA was defined as uniform acceleration for straight line segments. You can only use the term uniform whenever you have straight line segments.
Okay, I get
Yes.
it.
Beautiful. Shaptoshi.
Sir, we looked at two types of acceleration. One is acceleration at an increasing rate and one is acceleration at a decreasing rate, right?
Yes.
So acceleration at a decreasing rate, will it have a negative value?
Acceleration at a decreasing rate will not have a negative value. Whenever we use the term acceleration, we usually always mean speeding up. The word acceleration means speeding up, which means the value of the speed would be increasing. Earlier velocity would be smaller, final velocity should be smaller. Acceleration increasing means that object is speeding up, but it is speeding up more rapidly. And acceleration decreasing means object is still speeding up, but it is speeding up less rapidly. For example, DE is a segment of increasing acceleration. EF is a segment of decreasing acceleration. For both of these segments, the velocity is increasing. But for this segment, the acceleration was also increasing. So object was actually accelerating up. But for the segment of EF, the object was actually slowing down. I mean, if come to think about it, if I give you a physical explanation for the DEF part, for example, let's say this is the part a car was moving, and this is the part where the car did some braking, and it came to a lower velocity, and then they started to accelerate up. So the gas pedal was pushed down hard. So the car is now accelerating at a pretty high speed. So up to D to E, it has a really positive gradient of acceleration. But as the car speeds up, air resistance also starts to act up pretty strongly, which I discussed in the last class. That
Yes.
air resistance is essentially comprised of two factors: how fast you move, and how fast you move, because that affects for two factors: how fast you hit the air particles, and also how many air particles you hit per second. Okay, so it is possible that even when the accelerator is pressed all the way down, for this much duration of the time, the car's acceleration was actually increasing, but beyond a certain point, the air resistance becomes so strong that now the car cannot accelerate that much. So it is actually having its velocity increased, but at a certain point, the entire forward force produced by the engine has at this speed, the entire forward force produced by the engine has become perfectly cancelled out by the air resistance. So from this point onwards, you are having an influence. So this might as well be the top speed of that car, let's say 150 kilometers per hour or something like that for a regular car. Do I make sense?
Yes, sir, I got it.
Beautiful.
Sir, I have another question.
Yes, go ahead.
And my second question is that is it necessary that the car have to go through a constant speed between shifting from acceleration to deceleration?
No. The answer to your question is no. But you might also ask why.
Yes.
Yes, I get that point. Okay. Kids, for those of you who could not get that point, let me elaborate this is a good point. I mean, all the questions that I'm having from you kids are really interesting, and I really appreciate all of your participation, and I really mean it. So feel free to ask questions. I'm having a lot of questions from all the girls. The boys, on the other hand, are pretty quiet. I hope you finish enjoying the show and actually participate in the show. Just a second. What you just asked me, what Archie just asked me is that will the for the let me just elaborate the question, then I'll get into the explanation. For the acceleration to change from positive acceleration to negative acceleration, does it have to go through a segment of uniform velocity? That was your question, right?
Yes, sir.
Exactly. The answer I said was no. Why did I say no? Have a look. Try to have a good look for this segment of the graph. So I'm going to take this out. So I'm going to copy this and I'm going to take it over here. I'm going to superbly zoom in. So try to understand what is actually happening for this part. This is the segment, this is the point of motion where the velocity, where the acceleration changed from positive to negative. Do you think this is a continuous curve? Continuous curve means there is no horizontal part. I mean, this graph is a continuous smooth curve like that. It doesn't have a segmentation just like this. Let's say, for example, over here, and then a horizontal significant horizontal part, and like this. This graph is not like this. This is a continuous curve. So every single point over here on this curve, let me choose a different color. Every single point over here has an individual x and y coordinate. None of the x and y coordinates are similar unless they are on the either side of this thing. I mean, if you, whenever you are gonna move to the right side, you're gonna get, for the same y value, you're gonna get a different x value because this is starting to go down. Which means none of this entire graph has a horizontal part. Think about it. If you have a sine curve, try to think about it. Let me choose a bit thinner line. If you consider a sine curve has a shape like this, right? Whenever the sine curve actually changes its value from at the 90-degree position, do you think for a certain angle range, not value, do you think for a certain angle range it remains at 1, or it becomes exactly 1 at 90 degree? How does that work?
Sir, we aren't familiar with sine or cos curves.
I'll show you to make sense with you. Don't worry, just bear with me. What is son? Okay, so have a look at this graph. This might as well work for our purpose. So have a look. This is how a sine curve essentially look like. So this is the type of graph that I'm trying to talk about. So have a look over here. This is what we mean a continuous change. As you slowly increase the value of angle, the y value is also changing. This you can calculate from your calculator, or you can also go by the idea of trigonometry. But I'm not getting into the exact mechanism by which these values were plotted. I want you to consider the shape of this graph. Have a look. Every single point on this graph, no matter how much I zoom in, is exclusive. For one value of y, you would have one value. For example, I have over here 84.4 at 84.42 degrees, you have a y value of 0.9953. So if I slowly move it forward, you can see that we have exclusive values for every single point. There is no such point which is maintaining the same value for two different numbers. We're having exclusive values. What I mean by exclusive values, for one specific y value, you have one specific, for one x value, you have a specific y value. We could say that this graph actually does go through a small duration of uniform acceleration, uniform velocity. If there was a definitively horizontal line over here, there is no definitive horizontal line over here. No matter how much I zoom in, you'd always see that this line will always give you different points. See what I mean? But যদি আমাদের একটা পারফেক্ট একটা হরাইজন্টাল লাইন থাকতো তাহলে কি হতো, একটা সার্টেন সেগমেন্টের জন্য একই x কোঅর্ডিনেটের জন্য আমাদের different y coordinate, for different x coordinate, for different time values of the on the horizontal axis, we should have the same velocities or same y values, what I showed you over here. But that did not happen at this peak. This peak was achieved at an instance of time, something like it was going up and then starting to fall down. There was no hold position at the highest position. Did you get my point?
Yes,
sir.
Yes, sir.
So another example, physical example for this part to make visualization easier, I can tell you is this. For example, let's say you throw a ball vertically upwards. It starts to go up and slows down. It reaches to its highest position. Yes?
আপনি এটা শেষ করে 5-10 মিনিট একটু সময় দিতে পারবেন?
Oh, sure. I'll give you some time for my repair. Yes. So let's say I throw a ball vertically upwards. It starts to go upwards, and as the ball slowly goes upwards, it slows down, and eventually at a point it reaches its maximum height. At the point that we define as maximum height is where the upward velocity has become 0. immediately at that instant, the ball is going to start falling down. Now, it would not going to happen. It is not going to happen in a way that the ball is going to hold its highest position for a certain time duration. It's going to rise up and immediately fall down. If you wonder why, because the weight keeps on working on the object. The graph for a vertically upward thrown object might as well, the velocity time graph, not velocity speed time graph, the velocity time graph for a vertically thrown object might as well look like this. Let's say this is the upward velocity. You have thrown with this velocity. The object rises up for this point, and then it's going to be a straight line that cuts across the x-axis like that. This is what we mean by the highest point of the motion. So this is the upward velocity. As time goes by, the upward velocity slowly become less. So you have to understand, this is not the exact trajectory of the ball. This is the individual values of velocity plotted with respect to time. As time is going forward, the velocity is slowly becoming less, further less. At one instance, the velocity becomes 0. But what is the duration for which the velocity remains 0? What is the duration of for which the 0 was maintained? I mean, what I'm trying to say that this graph is straight. This graph is not like this. There is no such segment over here. No, this does not exist. So the duration for the zero velocity is also 0. It reached to a momentarily 0 rest position, and immediately it started to fall backwards. That's why we have a sharp cutoff on this x-axis. There is no common segment of horizontal section over here. Do you get my point?
Yes, sir.
But visibly, whenever we look at an object that is going upwards, it appears to our eye that the object actually stays at the highest motion for a little bit of time. That is the reason that the reason we have that kind of sensation is something that has to do with our optical memory. That whenever an object moves, we actually have the memory of that object to be in this position for about 0.1 second in our head. So whenever we move an object really fast, we do not see the object at every position. Rather, we sense the object's movement for every 0.1 second interval. This is also the reason why. This is also the reason that when a fan rotates pretty fast, we do not see the 3 blades individually. We rather see a shade of the blades. See what I mean? But this is also similar reason that whenever we throw a ball or object upwards, for example, let's say when the object is slowly just starting to reach its highest point, it becomes so slow that our eye registers that object to be stationary close to that position for a significant amount of time. But it is not actually stationary. If you videotape the object's motion with high-speed camera, you are going to see that the object is always moving. The speed of the movement might be very small, like very small, but it is never absolutely at stop for a duration of time. It remains stop for an instance of time, not for a duration of time. Try to distinguish these two phrases. Duration of time, which would be this, instance of time, like this.
So at this particular point,
Sir, I don't get it.
Excellent. Acha niche, heh bolo.
So at this particular point, the velocity will be 0. So the ball will stop for a certain instance, right?
Ball will stop for an instance, not for a duration. That's the point.
Yeah.
I mean, it's not gonna be is to go up and get stuck over there for a couple of seconds and then start gonna start fall. No, that's not how it works. It rises up and then falls down. Somewhere in between this motion, there is a point of time where the velocity reverses. That's where the v equals to 0 happens for an instance of time, not for a duration of time. That is the point that I'm trying to get in your head.
Sir?
Yes.
So this means that the constant period of velocity is so negligible that we don't show it in the graph.
It is actually 0. Our brain registers it to be a time because of the limitation of our memory of 0.1 second. It appears to us that the object got stuck in that position for a duration, but the object never actually gets stuck at a certain position for any duration of time. I mean, our brain sees it to be stuck at the highest position for a duration of time because of the limitation of our limbic systems. That's why I brought in the example for a high-speed camera, which has a much more sensitivity than our eyes.
Yes, sir, I got it.
Okay, we'll take a 5 minutes break for Maghrib prayer, although it's pretty past time, and then we'll resume class after 5 minutes. So yeah, 5 minutes break.
Okay, sir.
Yeah. So we are back from the prayer break. So resuming the lecture. So the point I was trying to make, did it make sense about did I get your question answered? কে করছিল? অরিত্রী, I guess, that would the
স্যার
object
আমি সপ্তর্ষি করছিলাম।
whoever of you asked, I forgot the name, but my point is that did you understand, could you grasp the idea that between the change from positive acceleration to negative acceleration, there would not be a duration of time for which an uniform velocity remains. There would be a time of maximum velocity, and that time instance represent from which point the acceleration is gonna start to reverse. Okay, I'll take further questions. Nur and Faiza.
Sir, in segment EF, what is the highest point? I'm confused.
F is the highest point.
Because the value of y is the biggest?
Yes, highest point always means that. E is the steepest point, whereas F is the highest point. I mean, in terms of steepness or gradient, E has the highest gradient and F has the lowest gradient. But in terms of the value of V, or high or low, E is the lowest point and F is the highest point.
Okay, sir, thanks.
Sure. Yeah, Adin.
সি আর ডিটা কি? সি থেকে ডি?
Yes. বলো, কোশ্চেন বলো।
সি থেকে ডি কি হবে? এটা কি অ্যাক্সেলারেশন নাকি ডিসিলারেশন?
Okay,
ডিসিলারেশন না?
It's definitely deceleration. And the gradient is how is the gradient changing? I mean, in terms of magnitude. At the C point, we have a pretty steep line, and at the D point, we'll once again have horizontal line, horizontal tangent. So the gradient is essentially decreasing, something like this that I did you over here for the reference. So for the CD part, we have deceleration, but the value of deceleration is decreasing. Okay, Wasifa.
So why is it decreasing the acceleration in the segment E to F?
I'm buঝিনি, আরেকবার please, sorry.
Why is it decreasing? From E to F, the velocity is increasing, right?
Yes.
Then why is the acceleration decreasing?
Because the gradient is becoming slowly smaller. And if you draw all the possible tangents over here, let's say, try to draw this thing. Over here, the tangent is going to be like that. Then if you slowly move to the right, you're going to have a tangent like that. Let's see, somewhere over here. And then if I try to draw over here, you might as well have a tangent like that, which might exist over here. So you're slowly losing gradient. This one is a more steep line compared to this one. Or I can say this one is a more slanted line compared to this one. I mean, this one will give you a larger gradient, for example, for out of a triangle like this. Whereas these triangles are going to give you even smaller and smaller gradient value because of the delta y by delta x ratio. And at the F point, the way I have tried to draw on the graph, that gradient is supposed to become 0 because as per my description, this part of the graph should have a 0 gradient, something like this. So the steepness of the graph is slowly becoming less and less and less, more or less.
Okay, sir, I got it.
Yes, Fabiha.
Sir, why can't we consider the line from D to E as a straight line? Like, why is it different from O to A?
Because we have a very visibly looking curve. I mean, O to A is a perfect straight line. I mean, there you can see a little bit of curve over here, which I didn't mean to work. I mean, I meant to draw this as a line starting from origin upward straight. So I meant it to be a straight line starting from origin from O to A, whereas D to E is visibly a curve. Okay.
Okay, sir.
So that was the part of the discussion that I wanted to talk about for a very so here what I essentially did, I mean, this is not essentially the actual velocity time graph for a specific given question, but I tried to incorporate all the different segments that I did discuss over here, 1 2 3 4 5 6, all of the 6 different line for different part of the velocity, so that you can actually understand how this kind of graphs can be properly explained. Now we have 40 minutes of time, and within this time I'm going to try to explain the exclusively the velocity and acceleration values for a parachutist graph. A parachutist graph is pretty simple to draw. So I'm going to try to draw this graph as accurately as I can. I hope I'll be able to do that. It as well is black. Okay, so let's say curve. Hey, no. Okay, so let's say this is the velocity time graph for a parachutist who is taking a fall from a high flying aircraft, and we are going to try to talk about how the resultant accelerations are working on him. Now for a parachutist, we need to consider a couple of forces. What are those forces? The downward force on the parachutist will always be weight, and we are assuming that the parachutist is gonna move through a uniform gravitational field. So we can pretty much consider that the weight of the parachutist is gonna be same to the entire fall and height. And but the air resistance is a thing that will be highly dependent on his velocity. So the air resistance is gonna be a variable. So we're gonna see what is happening. This is the point where the parachutist is taking his jump from a really high flying aircraft. So if I try to draw the alignment of the situation, for example, let's say this is ground. So this is just, let me just elaborate this a little bit, because I'm not seeing your participant list anymore because I had to use this part. Let's say this is ground and the parachutist is starting to take his jump from here. So let's say this is the parachutist. So you are seeing only the head, his entire body, torso, feet, and leg, everything is behind. So consider this round shaped object with two eyes and one mouth. This is the parachutist. You're only seeing his face and he's falling horizontally. So let's assume this is parachutist. So because I'm going to be using this figure multiple times, so I'm going to have him copy pasted over here. So let's say this is the point where the parachutist takes his jump, which means the aircraft was at this level and the parachute took his jump. And let's say when the parachutist was taking a jump, for the sake of easier visualization, let's assume that he was not in a plane. Let's say that aircraft was a high flying helicopter which was floating at a fixed level when he took the jump. Or if you consider for a airplane, actually an airplane, let's assume that the airplane was moving horizontally and the airplane did not have any vertical velocity. So it was not rising or falling. It was not gaining altitude or losing altitude. It was only moving horizontally. So the person, when the person took the jump, their vertical velocity was 0. This velocity time graph is essentially representing the vertical velocity of the parachute, is not the horizontal velocity. So let's say at the instance of jump, he just took the jump. So what we can assume that at this point his velocity is 0 and there is no air resistance, but weight will always be there. So let's say if I try to draw 5 different positions of the parachutist over here, let's say I'm going to try to draw 5 different positions. They don't have to be equally spaced, but I am trying to draw them equally spaced. Might as well be helpful. আচ্ছা পরে লাগলে আরো আঁকবো, সমস্যা নেই. So let me just label different points on the graphs over here just to go ahead with the discussion. Let's say this is our point O, and let's say this is our point A. Over here we have a point A. Over here we have a point B. Over here we have a point, the corner point is C. Then over here this is D. And let's say this is E and F. Now you might wonder, E আর F the same point হলো, একটু difference আছে আমি বলবো. So bear with me. Try to first understand how this whole thing is happening. If I go for the basic discussion of this graph, if I pull up these properties onto this graph, you can see over here, I mean, I have tried to represent that OA is an approximate straight line. Now, this is in a true scenario, this is never gonna be a straight line, because whenever the parachutist is gonna take their jump from the aircraft, as he's gonna start, as the parachutist starts their fall through atmosphere, they're definitely going to hit with air particles, and as long as they are hitting with air particles, there will always be some air resistance. But the way this part of the question is, this part of the graph is designed in our syllabus, is that for a small duration of time after the jump, the air resistance would be so small that we can consider it to be negligible. Consider it to be negligible. It is not actually negligible. It is not absolutely zero, but it will be too small compared to the other force involved. Namely, what is the other force? Weight. So one of the important part that is really important, let's say I'm going to draw the weight with a brown arrow, and this weight is gonna have the exact same size on all the positions. So the weight is not going to be different at all. So I'm going to use this weight arrow experienced by the parachutist for every position by equal magnitude. The only thing that is going to be varied is the air resistance. Let's say this is the value of weight that is experienced by the parachutist at all of his positions, which is not going to be a variable. Weight is same for everywhere. Remember this. And the other force should be air resistance. The resultant force should be coming from the vector sum of these two variables. Now, try to understand. For this entire process, in which direction is the parachutist falling?
Downward direction.
Downward.
Downward.
Okay, Sherin, you just asked me a question, but did you get your question answered? You asked a question in the chat window. I just saw it. Sherin Akhtar.
Yes, sir, I did.
Achha, okay, sorry. It was a pretty earlier question, but I just came to see this. Achha, so for the entire fall, the person is gonna go downward. So air resistance is definitely gonna go upwards. So I can essentially write, let's say, that the resultant force will always be, the resultant force on the parachutist will always be coming from weight minus air resistance, or it might as well come or air resistance minus weight. If you wonder, eta keno? Because we are gonna try to compare that which one is the bigger force, and the acceleration resultant force is always gonna be working in the same direction of the bigger force. So we're gonna try to compare these values. Now, kids, remember one thing that you need to remember from this figure: increasing velocity does not mean increasing acceleration. Increasing velocity can have decreasing acceleration. Similarly, decreasing velocity can have increasing deceleration. Do you see it?
Yes, sir.
মানে স্পিড বাড়ার মানে যে তার অ্যাক্সিলারেশনও বাড়তে হবে, ব্যাপারটা এরকম না. Speeding object can also experience lesser and lesser acceleration. উল্টাটাও হইতে পারে, but because acceleration is determined by how much force that person is experiencing. Velocity, on the other hand, is largely dependent on its initial velocity, or how much velocity did you start with. How much velocity did you start with? That is a very predominant factor to tell the how much speed do you have right now. I mean, so velocity acceleration comes directly from force by Newton's second law, F equals to ma. So that's the important bit. এটা আমি further discussion বলতেছি, but bear with me. So for the segment situation of O to A, আমি একটু বলে নেই, তারপর তোমাদের কোশ্চেন নিব. From the segment situation from O to A, we're going to consider air resistance negligible. So let's say this is our position O, and then O to A, air resistance is considered negligible, so there is no upward force. So the person is going to fall with uniform acceleration, and the gradient of this part, gradient of general symbol of m, let's say this gradient of this part is 10 meter per second square. I'm only writing the number over here because I don't want to clog up this part. Why is it 10? Because the value of gravitational acceleration is how much? 10. So
10.
For this part, we are assuming that the gradient is, we are assuming this is a straight line. Although it doesn't appear to be a straight line because I drew it to be a straight line, because I want to give you the idea that this part is being considered as a straight line. We are considering the resistance to be negligible, not zero. Negligible with respect to the other force that is involved. What is the other force? Weight. Acha. A is the point of the graph where the velocity of the parachutist has become significant enough that the air resistance is no longer negligible. So the air resistance is now starting to work. So this is the point where we are starting the air resistance to be increasing from zero. So এখান থেকে এই
এয়ার
পর্যন্ত
রেজিস্ট্যান্স নেগলিজিবল কেন হইলো সেটা বুঝতে পারলাম না.
it is considered to be too small compared to the weight. It is considered to be too small compared to the weight of the parachutist.
আচ্ছা আচ্ছা.
For this much duration.
হ্যাঁ.
So let's say from this point onwards, we are considering the resistance to be significant, or you can, as you might as well understand that in terms of numerical values, for this part the resistance was 0. This is the position where we are starting the resistance to be non-zero. So the resistance is starting its value from 0 over here, and it's going to slowly become higher as the velocity of the object, downward velocity of the object is slowly becoming larger and larger. So as the person speeds up, as the person is falling downwards, this air resistance is slowly gonna increase. So এখানে কি হবে? Let's say this is our O position. O থেকে A পর্যন্ত আমাদের uniform velocity আছে. A থেকে B পর্যন্ত আমাদের upward air resistance আস্তে আস্তে কি হবে? বাড়বে. So let's say this is our O. O তে শুধু weight আছে. Let's say this is our AB duration. So I'm trying to show the entire AB segment over here. If you wonder why the AB is shown as a single, I have a reason for this. What I'm gonna try to show you, let's say the air resistance is I'm gonna show the air resistance with a blue arrow. And initially the air resistance at position A, air resistance is 0. From A onwards, the air resistance starts to increase. So there will be a small air resistance. After a while, then the air resistance is going to be slightly bigger. Then the air resistance is going to be even slightly bigger. So air resistance is going to slowly start on increasing, and it's going to slowly become bigger. I shouldn't give too many arrows over here. It's becoming clumsy. So acha duta arrow this is duta arrow thak সমস্যা নাই. So this part of the graph is showing that the air resistance is slowly increasing. Now try to understand. For this entire segment, weight is still the larger force, and air resistance is slowly starting to increase from 0 to a higher value. Up to the B point, the value of the air resistance would slowly gonna rise equal to become W. So if I give you some numbers, which makes it always easier to understand, let's assume the weight of the parachutist is 100 Newton. Okay, as per this description, from O to A, for this entire segment, air resistance was considered how much? 0. And from A, the air resistance starts to increase. From A, air resistance starts to increase. So let's say from A to B, the resistance, I mean, as we go, I'm lacking structure. I might as well zoom it out. দেখা যাচ্ছে বলমান? মানে can I just see the stuff?
Yes, sir.
Yes, sir.
So let's say from A to B, the value of air resistance, this is going to slowly start to increase. So this is going to slowly start to rise up. So let's assume that at A position, the resistance was 0 and it's rising. So you have to understand that this W has a value of 100, which is a fixed value. And air resistance was initially 0. Then it's going to slowly start to increase from 0 and upwards. তাহলে 0 value টা আস্তে আস্তে কি হবে? বাড়বে. This 0 value is going to slowly increase. And as the value of this 0 is going to slowly increase, the subtraction result, which is the resultant force, this is slowly becoming less and less and less. Do you agree on this one? Check this out. Resultant force equals to weight minus air resistance, because these two forces are working in opposite direction. As the resistance gets bigger, slowly the resultant force will become smaller, which will essentially make the acceleration of the object smaller as well, because resultant force is given by F equals to ma. Mass of the person is small. So if the resultant force is becoming smaller over the journey from A to B, this acceleration also has to become what? Smaller. Do you agree to this one?
Yes, sir.
This is
Yes, sir.
Yes,
very
sir.
simple mathematics.
Yes,
So
sir.
this is exactly why you can see from A to B, the gradient of the graph is becoming less, because the acceleration of the parachute is becoming less and less and less. So he is speeding up. He's still falling downwards, but he's not speeding up as much as earlier. So every single second passes by, he gains speed, but he is not gaining speed as rapidly as he was gaining just the earlier moment. And B is the position as per the graph where the air resistance has become, so B is the position, at position B, air resistance has become exactly equals to 100 Newton. As a result, the resultant force has become 0, and then the acceleration will also become 0. As a result, we have a horizontal line, just a horizontal line. I know that it's 2 minutes past. I'm going to hold you just 2 minutes more, and then I'm going to close the class. Just give me 2 minutes more. So here we have a horizontal line because for this segment, the air resistance and the weight are perfectly balanced. This is what we call the first terminal velocity. At this point, the person is falling through atmosphere at a pretty high speed, like really high speed. And at that speed, he is having the weight perfectly balanced by the air resistance. And as a result, he is falling with uniform velocity. But this falling velocity is extremely large. If he hits the ground with this much velocity, he's going to disintegrate like an egg or something else. So this is not a safe velocity to drop to the ground. So what we are going to do? We're going to deploy the parachute. That's what happens at position C. At the C position, the person opens up the parachute. At the position C, the person opens up the parachute. Now, what happens after the person opens up the parachute? I'm going to continue my lecture from this point onwards next class. ঠিক আছে?
ঠিক আছে স্যার।
I have a
তোমাদের
question.
হ্যাঁ কোশ্চেন আমি আজকে না, কোশ্চেন তুমি একটু লিখে রাখো কোথাও, নেক্সট ক্লাসে অবশ্যই নিবা। I'm not going to hold you quiz further for today's class, but I'm going to go further through the discussion of this graph, and we're going to also try and do some math regarding this as well. I plan to do that. আর হচ্ছে I'm going to save this picture for today's class reference so that I can start with this exact point in the next class as well.
স্যার
Kids,
ম্যাথ কি এখানেই করব?
I'm going to show you some. I mean, you should have your copy and calculator and pen in your hands. I'm going to give the question over here. And as I'm going to go through, guide you through the process, you're going to do the calculation parts. Assume this is your blackboard and you are doing your class in the classroom. So what do? You copy the question in your copy and prepare for, yeah, that's how it's going to work out. Yeah. Kids, thank you very much.
Assalamu alaikum, sir.
Bye bye, sir.
Bye, sir.
Thank you, sir. Thank you, sir.